Okay, so this is going into a bit more detail on the mathematics of what is taking place here. And for those of you going for the higher grades, you will need to understand this. For those of you that want to take it a little bit easier, you could ignore this bit for now and you can come back to it later, or you can continue just to talk about in terms of there being a relationship between light intensity and the rate of photosynthesis. So this is something called the inverse square law. And as it says there, this states that light intensity is inversely proportional to the square of the distance from the light source. Now, you might be thinking, what does that mean? And that's understandable. So over the next few slides, I've tried to explain this in kind of simple terms and where this information comes from and what it actually means. So if you have a look at my fantastic diagram, there's a lamp, there is a meter ruler or a distance measure of 1 meter, 2 meter and 3 meter. And then there are some boxes and I'll get to those soon enough. So try to imagine that light is a physical quantity. So in fact, scientists do consider light to be a physical quantity and it's measured in little packages called photons. However, we don't need to worry about that too much at this stage, but try and imagine that there are certain quantities of light that can fall on an area. So if we have a look at the diagram at 1 meter, a certain quantity of light is going to fall on a particular area. If you had a way of measuring this, you'd be able to record how much light was falling on that area, and this is represented by the single square box on the diagram. Here, the light is relatively concentrated. We're very close to the lamp, so quite a lot of light is going to fall in that particular area. We would say there is going to be a higher light intensity. So as the distance from the lamp increases, so as we move towards 2 meters, the light's going to spread out. It's going to disperse. As you know from when you shine a torch, if you hold it very close up to a surface, you get a very small circle. As you move away from the surface, the circle will increase in its diameter. So the light is spreading out. So this now means on these 4 squares that the same amount of light that was landing on the single square at 1 meter is now landing over those 4 squares. If you measured how much light this would be, then this would be 1/4 of that is falling on the square that was 1 meter away, because there are now 4 squares that the light is being received by. This pattern continues, and if we go to 3 meters, as the area continues to get larger, we can see that that light is now spread out over a total area of 9 of those boxes. And if you measure the light intensity, which I've tried to illustrate with the colours, the closer you are to the lamp, the higher the light intensity. The further away you go, the less the light intensity is, and that's represented by the yellow becoming paler and paler as you move away. So from before, at 2 meters, if you have a look at the boxes, there are 4 boxes. So this means that the same light intensity that was falling on 1 box is now falling on 4 boxes. So if you could measure how much light was falling on each of those boxes, it should be 1/4 of the total amount that is there. So the light intensity at 3 meters is 1/9. This is because the amount of light that is falling on that area is now spread out between those 9 boxes in the diagram. So this is the same as dividing 1 by the distance squared. If you have a look at the blue box at the bottom, I've explained this in a little bit more detail. So at 2 meters, the square of 2 is 4. So if you divide 1 by 4, you get 1/4. At 3 meters, the square of 3 is 9. So the light intensity is now 1 divided by 9, or 1/9. And this would continue. If we had 4 meters on the diagram, it would be 4 squared, which is 16, so 1/16. So we come back to the inverse square law. So as it said on the original slide, it is stated that light intensity is inversely proportional to the inverse square of the distance. So this is basically just a fancy way of saying that as the distance increases, the light intensity decreases. If it was proportional to, it would mean as the distance increases, the light intensity also increases. But here it's inversely proportional, and we write that like this. So we've got light intensity, and then that little squiggle means proportional to, and then we have 1 over distance from the light source squared. And that relates to what we've been talking about over the last couple of slides, where you are dividing by a square of the distance. Mathematically, if we saw this on a graph, it'd be recorded as y equals 1 over x squared. This is where y and x relate to the variables on the different axes of the graph. So y is the variable on the y-axis, the dependent variable, and x is the variable on the x-axis, or the independent variable. And if we saw a diagram of the graph of the actual results, it would look something like this. So that's the inverse square law. That's what it means. That's where it comes from. And you need to be able to use that for the highest grades to be talking about why it is that the distance has the effect that it does on the light intensity.